I realize with these long problems, you're probably not done yet, but let's take a look at the first couple, and then I'll give you a few more minutes to work on number 3. This first one here is an example where we didn't factor the denominator for you. Most of the examples we've done so far, the denominator was already factored. Here, we're going to have to use some of our skills from the rational root theorem and Descartes' rules of signs to find roots and find factors of that so we can divide it out. So what we need to do is we need to take that x to the third minus 2x minus 4, and we need to find factors for it. Now this doesn't factor out real easily as it's written. There's no common factors, no grouping, so we're going to have to just kind of go brute force. First thing I'm going to do is put in that x squared term, like that. And then my rational root theorem tells me that if I take the coefficient of the constant term, in this case the -4, and the coefficient of my highest degree term, which is the x to the third, has a coefficient of 1, that the ratio of those gives me the possible roots. So the factors of -4 are 1, 2, or 4, positive or negative. And of course, 1 is 1. So I can have x plus 1, x minus 1, x plus 2, x minus 2, x plus 4, or x minus 4 are possible roots. I'm going to shoot in the middle. Let's see what happens if we use the 2. So if I try to divide by x minus 2 here, see if that is a root. Well, using synthetic division, I'm going to put on my coefficients. So I got 1, 0, -2, and -4. This is x minus 2, so I'm going to use a 2 here as my divisor. So I bring down the 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. -2 plus 4 is 2. 2 times 2 is 4. -4 plus 4 is 0. That is what we want. If this last number is 0, that means that that is a factor of that expression. So that means x minus 2 is a factor of x to the third minus 2x minus 4. So we need to divide that out to see what remains. This here actually tells us what that is. This is the constant term, that's the 2, it's a positive 2. This is the x term, that's a positive 2x. And this is the x squared term, so x squared. If you wanted to, you could take it in this form and divide out the x minus 2, you would get that same result. So what we have there now are factors. X minus 2 and x squared plus 2x plus 2. And of course, we still have 9x plus 2 in the numerator. The x squared plus 2x plus 2 is a quadratic. To see if that's factorable, remember, we can use that discriminant. The discriminant, remember, is b squared minus 4ac. If that is a perfect square, then this is factorable. Well, b here is 2, so that's going to be 2 squared. Minus 4 times a is 1 and c is 2. So it's 4 minus 8, that's a -4. That is not a perfect square, it's a negative, in fact. So that is not factorable. So what we have here, the 9x plus 2 over x minus 2, x squared plus 2x plus 2, is our factored form for the denominator. So now let's go ahead and write out the form of our decomposition. Remember, the linear term is just a number, a constant over the linear term. So a over x minus 2 plus, for the quadratic term in the denominator, x squared plus 2x plus 2, it has to be a linear numerator. So that's going to be bx plus c. And now we multiply this whole thing by this denominator, x minus 2, x squared plus 2x plus 2. So on the left side over here, our original fraction, the denominators just cancel out. Both the x minus 2 and the x squared plus 2x plus 2 cancels out, leaving us with x plus 2. When we multiply this by this next term, only the x minus 2 cancels out. So that leaves us with a times x squared plus 2x plus 2. When we multiply this third term, the x squared plus 2x plus 2 cancels out, leaving us with bx plus c times x minus 2. Any questions so far? So now on that right side, we have a little work to do. Here I'm going to distribute the a through that parentheses. So a times x squared is ax squared. A times 2x is 2ax. And a times 2 is 2a. Over here, I have to FOIL this out. Bx times x is bx squared. Bx times negative 2 is a negative 2 bx. C times x is cx. And c times negative 2 is a negative 2c. So now we have to group together things with like terms. On the right side, we have x squared. We have ax squared and bx squared. On the left side, however, we do not have an x squared. So that tells us that 0 is equal to a plus b. That doesn't mean a and b are 0. It just means whatever they are, they add up to 0. They're opposites. Then for our x term, on the left side, we've got 9x. So it's 9 is our coefficient. On the right side, we've got 2ax. We have a negative 2b x. And we have a plus cx. So 9 is equal to 2a minus 2b plus c. And then finally, for our constant term, on the left side, we've got 2. On the right side, we have 2a and a minus 2c. So this is our system of equations that we're going to work with. I'm going to use substitution here just because it's really easy with that top equation. 0 equals a plus b. If I solve that for a, I'm going to write as a plus b equals 0. All I'm going to do is subtract b from both sides. Gives me a equals a negative b, or opposite b. So I'm going to replace a in both of these other equations with opposite b. So this top equation here becomes 9 equals 2 times negative b minus 2b plus c. 2 times negative b is a negative 2b minus 2b plus c. And I'm going to combine the negative 2b and negative 2b. This is negative 4b plus c. So there's one equation in two variables. Now I'll substitute in for a in this third equation. So 2 is equal, instead of 2a, it's 2 times opposite b minus 2c. Simplifying that out, 2 times negative b is a negative 2b minus 2c. So there's my second equation. Now, in this equation over here, I notice all the coefficients are even. In fact, they're all 2. So I can divide that whole equation by 2 to get that 1 equals negative b minus c. So opposite b minus c. The reason I wanted to do that is now if I add that over here, 1 equals negative b minus c. I get 9 plus 1 is 10 equals negative 4b plus negative b is negative 5b. And c plus negative c cancels out. So 10 equals negative 5b. Solving that for b by just dividing by negative 5, I get that negative 2 equals b, or b equals negative 2. Now I can go back over here and find out what c is. 1 equals negative b is negative negative 2 minus c. So negative negative 2 is a positive 2 minus c. And at this point, you can probably see that c has to equal 1, but let's finish solving it. We subtract 2, you get negative 1 equals negative c, and we divide by negative 1. You get 1 equals c. So b is negative 2, c is 1, we need to find a. So if I go back up to this first equation I had, a plus b equals 0, or 0 equals a plus b. b is 2, or negative 2, 0 equals a plus a negative 2. I add 2 to both sides to get that 2 must equal a. So that tells us our partial fraction decomposition. For 9x plus 2 over x to the third plus, scroll up and see what that was. X to the third minus 2x minus 4 is a equals 2 over x minus 2 plus b was negative 2, so it's negative 2x. C is 1, so plus 1, over the x squared plus 2x plus 2. So there's our partial fraction decomposition. Anybody having difficulties with those? Any questions on that problem or any problems like it? Okay, example number 2 up here. Not going to go through the whole solution right now, but to solve it, you need to be able to factor that denominator. And to do that, you need to recognize that as the difference of cubes. X to the third is a cube, it's x to the power 3, and 1 is a cube, it's 1 to the power 3. The difference of cubes factors, this will be x minus 1 times x squared plus x plus 1. Once you have the denominator factored like that, now you can go about doing the partial fraction decomposition just like we did in that last example. So this would equal a over x minus 1 plus bx plus c over x squared plus x plus 1. And you can go from there. I'm going to give you guys a couple minutes to work on number 3 here, solving this system of equations. Even if you don't get completely finished with it, just want to see if you're going down the right track. I'm going to actually rewrite it for you down here. X times y equals negative 12. X minus 2y plus 14 equals 0. So I'll pause here and give you guys a couple minutes to work on it. Yes, sir.
Okay, it's Carter here. I'm just wondering, so the test corrections, they were due today, correct?
Yeah, if you need a little more time, though, I can give you till the end of the week.
Oh, okay. Yeah, I was just wondering if it's okay, because I don't have a scanner here. So if I just scan it, I guess today.
Yeah, that's fine.
Okay, cool.
Even if you need to take a picture of it with your phone even and send it as an, I still like it sent as an email, but you can take a picture with your phone and send it to my email. That works as well.
Okay, perfect. Thank you very much.
You bet.
Oh, what's it called?
Gamma scanner, CAMS, like scanner.
Oh, okay.
Camera scanner. It works really well, and you can just email it that way.
Okay,
Oh,
cool.
cool.
Yeah, no problem.
Okay, let's take a look at this problem here. Chances are you're not done with it yet, but there's a couple of different ways you can approach this. One way involves us using rational equations. You can solve this top equation for either x or y, but you're going to get something like x equals negative 12 over y. And working with that y in the denominator is tough to do. It can be done, but when we substitute that in for x down here, the only way to solve for it is to multiply through the y, and we'll end up with a quadratic equation anyway. So we just as well work with this bottom equation. I'm going to solve this for x. So to do that, I'm going to add 2y to both sides to get rid of the 2y. And I'm going to subtract 14 from both sides to get rid of the 14. So that gives me x equals 2y minus 14. Now we'll substitute that back into this original equation. So instead of x, I have 2y minus 14 times y equals negative 12. Now I have to distribute the y. Y times 2y is 2y squared. Y times negative 14 is a negative 14y equals negative 12. I'm going to move that negative 12 over so that everything's on the same side. Remember, quadratics are usually our first attempt. We try to set it equal to 0 and factor. So I'm going to add 12 to both sides. So I now have 2y squared minus 14y plus 12 equals 0. And to factor this, first thing I see is I can take out a common factor of 2. So if I divide each of those terms by 2, I have y squared minus 7y plus 6 equals 0. And finally, I'll try to factor this trinomial here. Y squared minus 7y plus 6 factors to y minus 6, and y minus 1 equals 0. So remember, when we have factors like that equal to 0, one of the factors has to equal 0. Well, 2 cannot equal 0. Y minus 6 can equal 0, though. Adding 6 will give us y could be 6. Or the y minus 1 can equal 0. Adding 1 to both sides gives us y equals 1. So y is either 6 or 1 or both. Let's double check it back up here in our equations to see what we get for values of x. So we'll try it up here. X equals, if y is 6, 2 times 6 minus 14. 2 times 6 is 12, minus 14 is negative 2. So if y equals 6, x would have to be negative 2. Let's test that in the first equation. Well, negative 2 times 6 does give us negative 12. That works. Let's try the y equals 1. So x equals 2 times 1 minus 14. 2 times 1 is 2. Minus 14 would be negative 12. So if y is 1, x has to be negative 12. Let's test that in the first equation. Well, x times y equals negative 12. Negative 12 times 1 equals negative 12. That works. So we have those two solutions here of negative 2, 6, or negative 12, 1 are the solutions for that systems of equation. Now, in this case, I tried to avoid working with that variable in the denominator. If we have time at the end of class, I'll show you a pretty radical example of those variables being in the denominator and show how we would solve and work through that. Let's get on to our new topic for today. We have worked with systems of equations. Now I want to look at systems of inequalities. So to review graphing an inequality, let's say we have something like 2x minus 3y equals 6. Or sorry, let's say not equals 6. Let's call it less than or equal to 6. We have to graph that. Now, in the form this is in, it's probably easiest for me to graph it using X-intercept and Y-intercept. The X-intercept is going to be the constant term, in this case 6, divided by the coefficient of x. 6 divided by 2 is 3. My X-intercept is going to be there at positive 3. My Y-intercept would then be the constant term divided by the coefficient of y. So the coefficient of y is a negative 3. 6 divided by a negative 3 is a negative 2. So that is my Y-intercept. So the line that represents this goes through those dots. And I really should double check the inequality symbol here. Less than or equal to means that numbers that are on the line are part of the solution. What that means is it can be a solid line like I have it drawn in there. Didn't draw it very straight though, so let me try that again. If that were strictly less than, or if that were just less than, then it would have to be a dashed line or a dotted line to indicate that the values that are exactly on the line are not solutions to that inequality. Now we've got the line on the graph, that's our boundary. But remember, to finish the inequality, we have to shade one side of the line or the other. We have to find which side of that boundary are solutions to this. Easiest way to do that is to pick a test point. I generally pick, if it's easy to locate, easy to tell which side of the line that it's on, I use the origin, 0, 0. just because that's usually pretty easy to test. So if I put that in here to test, 2 times 0 minus 3 times 0, is that less than or equal to 6? Well, yeah, 0 minus 0 is 0. That is less than or equal to 6, which tells us we're shading that side of the line. So points that are solutions to this inequality are any point on this side of that line, or since it's a solid line, any point that is on that boundary line. Let's try another one. Let's do 2y equals 4. Let's just do 4 minus x. I gotta forget, but 2y is greater than 4 minus x. So if we go to graph this, first thing we have to do is get y by itself here. This isn't in one of our standard forms, so we need to get it to a form that we can graph from. I'm going to divide by 2 to get y by itself. Y is greater than 4 divided by 2 is 2. Negative x I treat as negative 1x. Negative 1 divided by 2 is a negative 1/2 x. That can be graphed. My y-intercept is the positive 2. So 0, 2 there is my y-intercept. The slope is negative 1/2. So from that point, I go down 1 over 2. There's my second point. Now, because this is strictly greater than, the line I put through here cannot be a solid line. It must be a dashed or dotted line. So that line still represents the boundary values, but the fact that it's a dashed line is telling us that points that are exactly on that line do not satisfy this inequality. Now we need to figure out whether to shade above the line or below the line. So I'm going to pick a point and see if it's true. I'm going to use the origin again. Of course, the origin is 0, 0. If that is true, if that makes this inequality true, I will shade this side of the line. If the origin 0, 0 does not make this inequality true, I will shade the other side of the line over there. So let's test that point, 0, 0. So 2y becomes 2 times 0. Is that greater than 4 minus x becomes 4 minus 0? Well, 2 times 0 is 0. 4 minus 0 is 4. 1 is not greater than 4. So 0, 0 is not a solution. So that means we shade the opposite side of the line. Over here is the solution. Again, the dotted line tells us that points that are exactly on the line are not part of the solution. We can have other inequalities. We might have x minus 3 squared plus y plus 1 squared equals 9. Oops. Let's say less than or equal to 9. This is the equation of a circle. The center of that circle is going to be at 3, negative 1. Positive 3, negative 1. That's our center. Remember, the value subtracted from the x is the x coordinate. Value subtracted from the y is the y coordinate. This is the radius squared. So the radius is going to be 3. So from that point, we can go up 3, over 3, over 3, down 3. It is less than or equal to, so I can put a solid curve on my circle. Now I test. Either I'm going to shade inside the circle or outside the circle. Now here it might be a little close to try to test 0, 0. I mean, it is outside of the circle, but it might be a little close for comfort. So let's test the center of the circle. If I put 3 in for, that center is at 3, negative 1. If I put 3 in for x and negative 1 in for y, 3 minus 3 is 0, squared is 0. Negative 1 plus 1 is 0, squared is 0. Of course, 0 plus 0 is 0. Is that less than or equal to 9? And it is, which tells us we're going to shade the inside. Since that point is true and it's inside the circle, that means our solutions are the points inside the circle. So when our curve is a circle, the solutions can either be inside of the circle or outside of the circle. Or we might have x squared minus y equals 3x plus 4. Actually, I don't want equals in there, do I? Gotta make sure it's an inequality. Let's do greater than 3x plus 4. So we need to get this into a standard form. That would be getting y by itself. So I'm going to subtract x squared from both sides here. I have negative y is greater than negative x squared plus 3x plus 4. Now it's a negative y. I don't want that, so I have to divide by negative 1 to make that just a y. Now if I multiply or divide by a negative, I have to remember to flip the inequality sign. So negative y divided by negative 1 is just y. The inequality sign flips. Instead of greater than, it's now less than. Negative x squared divided by negative 1 is now a positive x squared. 3x divided by negative 1 is now a negative 3x. And 4 divided by negative 1 is now a negative 4. Now we have several strategies for graphing this. We know this is going to be a parabola. We could complete the square and get it into that, graphing form, or we could just find the roots. To find the roots, remember we put in 0 for y. We let it be equal to, and we factor the other side. X squared minus 3x minus 4 is x minus 4, x plus 1. Telling us that we have a root here where x minus 4 equals 0, which would be x equals 4, or at x plus 1 equals 0, which would be x equals negative 1. So we have roots at negative 1 and positive 4. That tells us our axis of symmetry is right between those roots. Negative 1 plus 4 divided by 2. Negative 1 plus 4 is 3, divided by 2 is 1.5. Our axis of symmetry is right here at x equals 1.5. Our vertex must be on the axis of symmetry. So if I put 1.5 in for x, back in, I'll go back to this inequality here because it's solved for y. If I put 1.5 in for x, I will get the y-coordinate of the vertex. So y is less than 1.5 squared minus 3 times 1.5 minus 4. 1 and 1/2 squared is 2.25 minus 3 times 1.5 is 4.5 minus 4. I should have used equals in here for right now to find the vertex. 2.25 minus 4 is negative 2.25. Sorry, 2.25 minus 4.5 is negative 2.25. Minus another 4 is a negative 6.25. That's telling us our vertex is here at x is 1.5 and y is a negative 6.25. Now, this equation here is strictly less than, so that tells us that our graph has to be dashed. So we draw in our parabola with a dashed line. So once again, either we color in inside the parabola or outside the parabola. The origin here, 0, 0, is clearly inside the parabola. So let's put that in and see what we get. We put that into the original equation here. 0 squared minus 0 equals 3 times 0 plus 4. Well, it's pretty easy to see. 0 squared minus 0 is 0. 3 times 0 is 0 plus 4 is 4. 0 is not greater than 4. So the origin is not a solution. So since that was inside the parabola and it was not true, that means we must shade outside the parabola. So that is the solution to that inequality. Any questions there? We have 1 minute before break time. So I'm going to put an example up here. I want you guys to graph it. X plus 2 squared plus y minus 3 squared is greater than 16. Want you to start working on that. We'll take our break here in about a minute, and then we will look at that after break. I'll give you time during break to work on it as well. So if we graph this, this is the equation for a circle. So it's at center is at negative 2, 3. So negative 2, 3 is right there. R squared equals 16, so that tells us that the radius equals 4. So down 4, over 4, up 4, over 4. It is strictly greater than, which tells us that this is a dashed curve, dashed circle. I'm not great at drawing solid circles, so my dashed circles are even worse. Now we have to figure out whether the points are inside the circle or outside the circle. The origin is definitely hard to tell whether it's inside or outside the circle, so we can't really use the origin. So when we're dealing with circles, again, the center of the circle is often an easy point to use. So let's use that negative 2, 3. So if x is negative 2, that becomes negative 2 plus 2 squared. If y is 3, that becomes 3 minus 3 squared. And let's see if that's greater than 16. Well, negative 2 plus 2 is 0, squared is 0. 3 minus 3 is 0, squared is 0. Well, 0 plus 0 is not greater than 16. So this point, the center of the circle, is not a solution. So since that's not a solution, that means the solutions can't be inside the circle. They must be outside the circle. So we color in outside of the circle as our solutions. So any point that's outside that circle is a solution. The dotted curve on the circle tells us that points that are exactly on the circle are not solutions. So now our next step is we could look at systems of inequalities. We might have 4x minus y equals 2, and, or sorry, less than or equal to 2. 4x minus y is less than or equal to 2. And we might have 2x plus 3y is greater, let's go 6. So we need to graph both of these inequalities. When it comes to systems of inequalities, the graph is the best solution, the best way to express the solution. So the first one up there, I can use X-intercept and Y-intercept if I would like, since it's in that form AX plus BY equals the constant. The X-intercept is the constant divided by the X coefficient. 2 divided by 4 is 1/2. There's my X-intercept. The Y-intercept is the constant divided by the Y coefficient. So 2 divided by -1 is -2. There's my Y-intercept. The inequality is less than or equal to, which means the or equal to means it's a solid line. The origin, it's close, but it's obviously on the left or upper side of this line. So let's test that 0, 0 in. So if x is 0, that's 4 times 0 minus y is 0. Is that less than or equal to 2? Yes. 0 minus 0 is 0. That is less than or equal to 2. So I'm going to shade this side of that line. That's the side that my origin was on. That point was true, so we shade that side. The second inequality here, again, I graph the equation of the line first. So what I'm really graphing for the line is 2x plus 3y equals 6. Once again, it's in that form ax plus by equals c, so I can graph it using x-intercept and y-intercept. My x-intercept will be 6 divided by 2, that's 3. My y-intercept will be 6 divided by 3, that's 2, right there. Now this is strictly greater than in my inequality, telling me that's a dashed line or dotted line. I'm going to test my origin again. The origin is obviously below that line, so let's test 0, 0. Putting it into the original inequality. So 2 times 0 plus 3 times 0, is that greater than 6? Well, 2 times 0 is 0. 3 times 0 is 0. 0 plus 0 is not greater than 6. So the origin is not a solution. Since that does not make it true, it's the other side of the line that's colored in. So the origin's over here, we color in the other side over here. So the solution to this system of inequalities is the overlap in the shaded areas along with the boundary conditions. This is a dashed line over here, a solid line here, and the overlap is in this region up here. So that section of the graph contains all the solutions that make both inequalities true at the same time. Our inequalities do not have to be linear inequalities. We could have y is greater than x squared minus 2x minus 3. And we have 2x minus 3y let's go is less than or equal to 6. So for the first one up here, we need to graph, first of all, that parabola y equals x squared minus 2x minus 3 to get our boundary. We're going to do that by setting y equal to 0 and factoring. So x minus 2 or x squared minus 2x minus 3 is x minus 3 x plus 1. Solving each of those, x minus 3 equals 0 gives us that x equals 3. Positive 3 here. X minus 1 equals 0, or sorry, x plus 1 equals 0 tells us x equals negative 1, so right here. Our axis of symmetry then would be exactly between them at x equals 1. So we put 1 into this equation to find the y-coordinate of the vertex. So y equals 1 squared minus 2 times 1 minus 3. So that's 1 squared minus 2 minus 3, which equals negative 4. So 1, negative 4 is the coordinate of our vertex. So that's enough to sketch our parabola. This is greater than, so our parabola is dashed. We either need to shade inside the parabola or outside the parabola. 0, 0 is inside the parabola, so let's put that in. So y is 0, x is 0. Well, that's saying 0 is greater than negative 3, which is true. So that means we shade inside the parabola. So that's where this is all shaded up. Next, we graph the line. So 2x minus 3y is less than or equal to 6. We're going to graph the boundary. 2x minus 3y equals 6. Now we could do the intercepts if we wanted to. 6 divided by 2 is going to be positive 3. 6 divided by negative 3 is going to be a negative 2. Those are our x and y intercepts. Or we could solve this and put it into slope-intercept form. Let's do that just to show that we get the same equation here. We subtract 2x, negative 3y equals 6 minus 2x. We divide by the negative 3. Y equals 6 divided by negative 3 is negative 2. Negative 2x divided by negative 3 is a positive 2/3 x. So we have our y-intercept at -2, so 0, -2, and the slope of 2/3 tells us we go up 2 over 3 to get to that next point. So notice we get the exact same 2 points graph. This is less than or equal to, so it's a solid line. Let's test the origin again. The origin is obviously on above the line, above and to the left. So let's put in 0, 0 here. Well, 2 times 0 is 0, minus 3 times 0 is also 0. 0 minus 0 is less than or equal to 6. So since that point is true, that is the side of the graph that we shade. So our overlap here with its boundary conditions, we have the boundaries of the parabola here, which are dashed, of the line here, which is solid, the parabola here, which is dashed, and we're shading in the middle. Right here. So that is the solution to that set of inequalities. I'm going to have you try one in your notes here quick. X minus 2 squared plus y minus 1 squared equals 25, or sorry, is less than or equal to 25. And y is greater than 1/2 x minus 2. Graph each of those inequalities, find the overlap, find the solution, that system of inequalities. I'll give you a few minutes and then we'll go. So the first shape here is a circle with a center at 2, 1. So right there, r squared equals 25, which means the radius is 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Why are my scales way off? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It is less than or equal to, so it is a solid curve. Pretend that looks like a circle and not an oval. A really ugly oval at that. Anyway, we need to test to see if it's inside or out. I'm going to test the center. Now, if you haven't figured out by now, testing the center makes this 0 and this 0. 0 is less than 25. So the center is true. So we shade the center of the circle. Oops, wait for a word to kick back on here. Maybe. So we've shaded inside the circle. So now we got to do the line here. Well, this line is set up fairly simple to graph. It's of that form. And we look at it as y equals 1/2 x minus 2. So we start at -2. And from there, our slope of 1/2 means you go up 1 over 2. So that's where our second point is. Get that out of there. It is strictly greater than. So this is going to be a dashed line. Let's pick the origin here, 0, 0, and test it. Is 0 greater than or equal to 1/2 times 0 minus 2? Well, I get 0 is greater than -2. That is true. So we are shading above the line. So our overlap here, we'll do in black. Our boundary is this solid portion of the circle from there to there. Then this dashed portion of the line here, and everything in the middle. So that enclosed region is the solution to this system of equations. So if you can graph equations, graph lines, parabolas, and circles, graphing the inequalities isn't that difficult. You just have to decide if it's solid or dashed curve, and then which side to shade by testing a point. The systems of inequalities then kind of follow along the same line. Graphing is the only way that we are going to solve systems of inequalities. Now, with systems of inequalities comes a concept called linear programming. Linear programming deals with maximizing and minimizing. So in other words, we're trying to find a value that's as large as possible or as small as possible. When we're dealing with linear programming, there is an objective function. The objective function is stating a relationship that we want to make as large or as small as possible. For our examples here, we're going to be looking at maximizing. So let's say that we want to maximize the objective function. Z is our objective variable here. That's the value that we want to maximize. So it's not really part of the graph. 2x plus 3y. So we want to find the values of x and y that maximize z within given constraints. These constraints limit the possible values of x and y that we can use. And these constraints take the form, generally, of a system of inequalities. So for this objective function, I'm going to give us several constraints, 4 constraints. First 2 are relatively straightforward. X has to be greater than or equal to 0. Y has to be greater than or equal to 0. So what that's saying is if I look at my graph, I am only looking at that first quadrant here, where both x and y are positive. I could graph those inequalities. Here is x equals 0, so it's going to be shaded up here. Here's y equals 0, greater than means it's going to be shaded over here. Obviously, our other 2 objective functions are going to help us enclose this region. And generally, we do want to completely enclose a region, so it will, or sorry, our other 2 constraints will help us enclose this region. And generally, we have at least 3 constraints so that we can completely enclose a region. So our third constraint is going to be 2x plus y is less than or equal to 8. Notice, by the way, that all these are less than or equal to. If they're strictly greater than or less than, it causes issues with maximizing the function. So to graph that, we'll do that in purple. 8 divided by 2 gives us an X-intercept of 4. 8 divided by 1 gives us a Y-intercept of 8. So my line goes through those 2 points. If I test the origin here, 0, 0, 2 times 0 plus 0, is that less than or equal to 8? Yes, 0 is less than or equal to 8. So this is going to be colored in here. So basically we've limited ourselves to that triangle so far. I'm going to get rid of some of these colorations out here because we know it's not out there anymore. We're inside that triangle. But we have a fourth constraint here. This fourth constraint says 2x plus 3y is less than or equal to 12. So again, let's use our intercepts here. 12 divided by 2 is 6. So the x-intercept is 6. 12 divided by 3 is 4. So the y-intercept is 4. Less than or equal to again, so it is a solid line. If we try 0, 0, 2 times 0 plus 3 times 0, well, 0 is less than 12. So it's definitely below that line that we're coloring in. So this is telling us that the region that we are interested in is this region right here. So linear programming, one of the theorems that we're not going to prove, we're just going to accept this one. Linear programming tells us that the maximum or minimum value of that objective function will be at one of the vertices of that shape created. This creates a polygon. So one vertex here is 0, 0. This one up here is 0, 4. That was the y-intercept of this fourth equation. This point here is 4, 0. That was the x-intercept of this equation. We need to find where those two cross. Well, it looks to me like that is at 3, 2. Let's test that to make sure it works. I put in 3 and 2 here. 2 times 3 is 6 plus 2 is 8. That works. How about here? 2 times 3 is 6 plus 3 times 2 is 6. That makes 12. So 3, 2 is the location of that corner. We have to test each of those vertices into that objective function. Remember, an objective function up here is z equals 2x plus 3y. I'm actually going to put it off to the side over here a little bit. So I'm going to test 0, 0. Well, 2 times 0 plus 3 times 0, that just gives us 0. That's definitely a minimum, not a maximum. Let's test 4, 0. 2 times 4 plus 3 times 0. 2 times 4 is 8 plus 0 is 8. Well, it's better than the 0. We're better than the first point. Our third point is the 3, 2 over here. Let's test that. So that equals 2 times 3 plus 3 times 2. 2 times 3 is 6. 3 times 2 is 6. That adds up to 12. That's our best one so far. Let's test our final point, which was 0, 4 here. So that's 2 times 0 plus 3 times 4. 2 times 0 is 0. 3 times 4 is 12. That also adds up to 12. So what this is telling us is that either of those two choices, either x is 3, y is 2, that'll give us an objective value of 12, or x is 0, y is 4 will give us an objective function value of 12. So those both give us maximum values of the function. This one here gives us the minimum value, but that wasn't what we were looking for. So what's a practical situation where we would use something like this? Well, it's used in business all the time, but some of those constraints get to be pretty complex. Let's go ahead and take a look at a little bit simpler but more realistic solution. Let's say a student earns for work study can earn $15 per hour for tutoring, or they can earn $10 per hour working as an aide. So we're going to let X be the number of hours worked as a tutor, and Y be the number of hours worked as an aide. So our objective function here, which is the amount of money this student earns, Z is equal to 15 times X plus 10 times Y. $15 an hour times the number of hours spent tutoring, plus $10 an hour times the number of hours working as a teacher's aide. Our constraints. The first one, it tells us the student is bound by the following constraints. To have enough time for studies, cannot work more than 20 hours per week. So X plus Y is less than or equal to 20. So if you're going to graph that, this is 20, this is 20. X plus Y is less than or equal to 20. We graph that across there, we're shading inside there. Now notice I didn't go past the axes when I shaded. It's implied here that you can't work less than 0 hours a week. So the axes are also a constraint. Tutoring center requires each tutor to spend at least 3 hours per week tutoring. So the tutoring X has to be at least 3 hours. So X, 1, 2, 3, shaded on this side. The tutoring center requires each tutor to spend no more than 8 hours a week tutoring. So X is less than or equal to 8. So somewhere in here is X equals 8. And it's on this side. So those are the only constraints we have. So we're looking at this polygon here. So our vertices, this here would be 8. If you do the math in this top equation, you'd come up with y have to be 12. This here would be at 3. Y would have to be at 17. This is 3, 0. And this is 8, 0. Well, the 3, 0 and 8, 0 are not going to maximize the pay. They're going to minimize the pay. 3, 0 would most likely be the minimum pay. So it's going to be one of these two that maximizes the pay for that objective function. So Z equals 15x plus 10y. Let's try 317. X equals 3, y equals 17. So we have 15 times 3 plus 10 times 17. That's 45 plus 170. That'd be $215 per week. The other point over here was 812. Let's try that. That's going to be 15 times 8 plus 10 times 12. 15 times 8 is 120. 10 times 12 is also 120. Adds up to 240. So the best allowable combination of hours, 8, 12, remember 8, the X was the hours tutoring. So we spend 8 hours tutoring and 12 hours as an aide. Any questions? Okay. Our computer system's going nuts here. I don't know if any of you guys had something pop up on your screen there about Alertus. You did, okay. That is the WITC emergency alert system. I would get a notice if they were actually running a drill, but that did say a test, not a real situation. You notice on it did say this is a test, so that means it wasn't any sort of emergency we needed to address. So I plowed through it. But normally, if that comes up, that means we are supposed to go into, some sort of emergency response situation. Those of you at home that you're safe where you're at. Those of us in the building are supposed to, seek some sort of a safe shelter when that comes up. But it was an alert, and it's been malfunctioning lately. I've been getting those actually on and off for a couple of weeks, so there was no concern there, just so you know. Okay, I think we have absorbed enough new material for the week, so I promised you that if we had some time at the end here, I would go back and talk about, we solve for X and Y in a very weird situation before. I want to talk about how would we solve for X and Y if we had an equation like 3 over X squared plus 1 over Y squared equals 7. This is an extremely tough equation to solve for one of them. And actually, I shouldn't say it's not tough to do, it's tough to see how to approach it. Anytime I have a variable in the denominator of a fraction, I get it out of that denominator by multiplying by a least common denominator. Now here my denominators are X squared and Y squared. My least common denominator is going to be the combination of those two denominators multiplied together, X squared, Y squared. So this is very similar to the calculation we did with our partial fractions. We distribute the X squared, Y squared. On this first term, the X squared cancels out, leaving us with 3Y squared. We distribute it here. On this next term, the Y squared cancels out, leaving us with 1X squared, or just X squared. Equals, now we have to remember to multiply the other side of the equation as well. 7 times the X squared, Y squared is just 7X squared, Y squared. That was the easy part. Now we have to try to figure out how to isolate one of those variables. This term here where the X and the Y are together makes it really difficult to separate them. So what I'm going to do is I'm just going to pick one of these to move over. I'm going to move the X squared over. So I have the Y squared by itself on the left side. I'm going to subtract X squared from both sides. So I have 3Y squared equals 7X squared, Y squared minus X squared. Now on the right side of this equation, I have the opportunity to separate the X squared from the Y squared by factoring. So I'm going to leave the right side of this, or the left side of this equation as it is, 3Y squared. On the right side, I have a common factor of X squared. I'm going to factor that out. If I divide this whole thing by X squared, what I'm left with is 7Y squared minus 1. That negative X squared divided by X squared is just a negative 1. You might be looking at that wondering, how is that simpler? Well, now we can isolate that x by dividing, actually, we're isolating the x squared first, by dividing by 7y squared minus 1. That'll cancel that out. Over here, we divide by 7y squared minus 1. So what we now have on the left side, 3y squared over 7y squared minus 1 equals, on the right side, all that's left is x squared. Our last step to solve for x, to get rid of the squared, we square root. So the square root and the squared cancel out. That gives us x. And that's going to be equal to the square root of 3y squared over 7y squared minus 1. Oops. Now I realize that is not a pretty solution for x, but it is a usable solution for x. If this were a system of equations, now we would be able to substitute that back in for x in the other equation. Hopefully the other equation involves some sort of an x squared. Okay, so I think we've had enough new material for the day. So remember, there's an old homework assignment. From Monday that'll be due tomorrow. There is a quiz that is off the material from last Wednesday and this Monday that's due Friday. And then, of course, the homework from today's material I believe that's homework, what is that, 9A? That'll be due next Tuesday. Now, with that in mind, we have homework 9A is sitting out there. Actually, that's, yeah, because 8B is the one that is due. Homework 9A is sitting out there. That means we are starting week 9 today. So that means 2 weeks from last Monday, or a week from this next Monday, is our second unit test already. That would be coming up on November, come on calendar, November 11th will be our next unit test, our next midterm. Did you guys have any questions? Okay, you guys have a great day, have a great weekend, and we'll see you next Monday.